Hello, my name is Kevin Craig. This is a presentation on the Mechatronics Studio introductory exercise. In the first part, you will be making multimeter basic measurements. You will check breadboard continuity. You will set DC power supply voltages to plus and minus 15 volts and measure those voltages. You will measure the 5-volt output, which is fixed. You will measure resistance, compare what you measure to the color code, and note the tolerance. You will use a potentiometer, first as a variable resistor, and then as a voltage divider. You'll measure the capacitance of 3 types of capacitors: ceramic, electrolytic, and tantalum. You'll measure inductance. You'll check the operation of a diode. You'll check the operation of a transistor, a metal oxide semiconductor field effect transistor, a MOSFET. And then you will check the operation of the 741 operational amplifier. We will put the amplifier in a buffer configuration where the input equals the output. You will use your multimeter to check the continuity of the breadboard. The setting on the multimeter is shown for continuity. The green lines indicate holes that are connected. The red lines indicate holes that are not connected. You can see in this main portion of the breadboard, there's continuity in the rows. There's no continuity in the columns. And across this divide or trench, there's no continuity from one side to the other. In the regions which we call the rails, there's continuity in a column, but not continuity in a row. We use these rails typically for voltages and ground. This is the DC power supply you will be using for all your Mechatronics Studio exercises. This power supply has a constant 5-volt output with a maximum current of 3 amps. It also has a adjustable plus or minus 15-volt output with a maximum current of 1 amp. This adjustment is coarse. If you are using both sides of the power supply for a particular exercise, since there can be only one ground, and the ground of the 5-volt power supply and the ground of the plus or minus 15-volt power supply are not the same, you need to connect these two grounds with a banana cable, as I've done here. Shown here is the breadboard you will build with all of its components. I need to bring power into the breadboard. There are 4 terminals on the breadboard. I use them for plus 15 volts, minus 15 volts, 5 volts, and ground. I connect the power to these 2 power rails at the top of the breadboard, which are separate from the main portion of the breadboard. The 15-volt voltage goes to this red portion of this power rail. The minus 15 volts goes to the power rail, the red column on this power rail. The ground goes to the blue column on this power rail. And since I only have 2 power rails and I need to bring 5 volts to my breadboard, I'll bring the 5 volts directly to this power rail on the main portion of the breadboard. I then need to bring the plus or minus 15 volts and ground to the main portion of the breadboard. I do that with these breadboard hookup wires, and you can see I bring minus 15 volts to this column on this power rail. I bring plus 15 volts to this column on this power rail, and I bring ground to the blue column on this power rail. So I don't have to bring the ground from the upper portion to each of these power rails. I use breadboard wires at the bottom to connect this ground to this ground to this ground. So on these three power rails, the grounds are all connected. This power rail has plus 5 volts. This power rail has minus 15 volts. This power rail has plus 15 volts. And you can see that enlarged over here for the connections and also for the ground wires. I need to then mount noise suppression capacitors. I have the 3 ceramic capacitors, which are not polarized, and I have the 3 electrolytic capacitors, which are polarized. Again, the positive leg needs to go to the positive voltage on the plus 5 volt and plus 15 volt power rails. On the negative 15 volt power rail, the plus lead of the electrolytic capacitor will go to ground, and the then other leg will go to the minus 15 volt column on this power rail. Once I have the voltages all on my main portion of my breadboard, I then need to measure these voltages to make sure I'm getting the actual voltages to the breadboard, because there could be a problem in going from the terminal to these power rails, and then from these power rails to the main portion of the breadboard. And if you don't get these voltages on the main portion of your breadboard, you need to then go back and determine where the problem lies. There could be a bad connection at the terminal. There could be a bad hookup wire in going from the upper portion to the main portion of the breadboard. So that needs to be checked. Then you can mount your components. Here we mount our resistor. So the 2 leads, again, are not shorted, and I've chosen to mount this resistor across the divide. When we make measurements, we never make measurements on the actual leads from the component. We use hookup wire attached to the mini grabber on the multimeter to make our measurements. And you will see that in the video that shows the actual performance of these measurements. So here we have a resistor. Here we have a potentiometer. Again, it's mounted vertically, so each of the legs has its own row in this breadboard. Here's the potentiometer laying on its side, so you can see its 3 legs. This is a simple U connector that's used to connect two rows together that we will need when we use the potentiometer as a variable resistor. Here are 3 capacitors, electrolytic, tantalum, ceramic. The ceramic is not polarized. These 2 are polarized, so when you make the measurement, you need to connect the red lead from the multimeter to the positive lead from the capacitor. This is an inductor, and again, there are 2 legs to the inductor. You can't see them. There's a picture in the notes. And you measure inductance across those 2 leads. This is a diode. The diode only conducts current in one direction. So if you apply the positive lead and the negative lead from your multimeter, so you're measuring the direction of current flow, you will read a positive voltage drop. If you reverse the leads, then you will read overload, which means there's no current flowing in the opposite direction. It's like a check valve in hydraulics that only allows fluid to flow in one direction. Here's your MOSFET, your metal oxide semiconductor field effect transistor. It has 3 legs, and I've mounted it again vertically, so each of the legs has its own row and are not shorted together. Here's my 741 operational amplifier. I show it here with its 8 legs, and here I've mounted it in the buffer configuration, where there is no connection where the op amp is mounted so that its little indicator for the top of the op amp, here I've mounted it upwards, and then the pins are named 1 through 8 in a counterclockwise fashion. For the buffer op amp configuration, there's no connection to 1. Pin 2 is connected to pin 6. Pin 3 is an input, your non-inverting input, while pin 2 is called the inverting input. So pin 3 I connect to my 5-volt rail. Pin 4 is connected to minus 15 volts. There's no connection to pin 5. Pin 6 is the output, which for the buffer configuration is connected back to pin 2. And you read the output there, and we should read 5 volts since this is a buffer op amp configuration where the input then will equal the output. Pin 7 there is connected to plus 15 volts, and there's no connection to pin 8. Here we see the resistor you will be using. This is a 5-band resistor. There are 5 rings around the resistor. We note the colors: green, blue, black, orange, and brown. These are associated with numbers as shown on this reference card, which is also shown in your notes. The first 3 numbers indicate the value of the resistor. Here it's 5, 6, 8. The fourth color is orange, which indicates a multiplier of 1 kilo ohm. So the resistor prediction is 568,000 ohms, or 568 kilo ohms. And the tolerance, the brown color indicates plus or minus 1%. When I measure the resistor using my multimeter, I get 568 kilo ohms. So my measurement compares exactly with the prediction. Of course, there is a tolerance, plus or minus 1%, and there's no indication of what the power rating of this resistor is. I know it's a 1/2 watt resistor from the documentation that came with the resistor, but we need to then, if there's no documentation, you can tell what the power rating is from the size of the resistor, as I'll show on the next slide. Here we see a picture of a resistor. To determine the power rating, we need to measure the resistor, its lead length, lead diameter, length, and diameter of the resistor. And we see here for these various measurements, we see that we can determine whether the resistor is a 1/8 watt, 1/4 watt, 1/2 watt, or 1 watt. In any of the exercises in the Mechatronics Studio, we typically use resistors that are 1/2 watt or perhaps a 1/4 watt, nothing larger. This is the potentiometer that we will be using in our exercise. The potentiometer has 3 legs. The nominal resistance of the potentiometer is the resistance between legs 1 and 3. By turning this screw, you can adjust the resistance between legs 1 and 2 and between 2 and 3. However, those 2 resistances will add up to the resistance between legs 1 and 3. This middle leg is called a wiper, and it mechanically moves left and right within the potentiometer. To use this potentiometer as a variable resistor, we use that that small U pin to connect pins 2 and 3 on the breadboard. We measure the resistance between pin 1 and 2, and then we turn the screw to adjust this resistance while we're measuring it. The variable resistor is then between pins 1 and 2. To create a voltage divider using this potentiometer, we will connect pin 3 to ground. We will connect pin 1 to a voltage source. We will measure the voltage at pin 2, and then we can turn the screw to adjust the voltage at pin 2. Pin 2 voltage is the voltage divider output, which is given as the voltage that we supply. We call it E1, and it's the voltage that we measure then is equal to that supply voltage times the resistance between pins 2 and 3, divided by the sum of the resistances between pins 1 and 2 and between pins 2 and 3. This is using the potentiometer as a voltage divider, and we explained how the potentiometer can be used as a variable resistor. Shown are the capacitors that you'll be measuring the capacitance of. This is the ceramic capacitor. It's not polarized. On this capacitor, the number 154 means 15 with 4 zeros, and the unit is picofarads. So 150,000 picofarads, which will equal 150,000 nanofarads. Nano is 10 to the minus 9, and that's equivalent to 0.15 microfarads, 10 to the minus 6 farads. This is a tantalum capacitor. It's polarized. The legs are the same length, and the positive leg is indicated on the capacitor housing. This is an electrolytic capacitor. It's polarized. It usually has 2 legs of different length. The longer is the positive leg, but often the legs are clipped so the component can sit flush with the breadboard. And so on the housing of the capacitor, there is an indicator for the negative terminal. Shown is the inductor that you'll measure the inductance of. An inductor is simply a coil of wire with a core. In our case, the core material is air. This is an air core inductor. This is the picture of the inductor you'll be measuring. It has 2 terminals, and you'll measure the inductance, and the unit is Henry. Shown is the diode you will be measuring. The diode has a white band on it to indicate the direction of current flow. The current flows from the left to the right. So we will use the diode check function on the multimeter. This is the schematic representation of a diode, and you can see the arrow indicates the direction of flow, and this vertical line indicates that no current can flow from right to left. To check the diode, you'll connect the red probe to wire 1, the black probe to wire 2, and you should view approximately 0.5 volts as the voltage drop as current is flowing from 1 to 2. If you connect the red probe to wire 2, the black probe to wire 1, you'll view on the multimeter an indication for overload, which simply means no current is flowing. This is our MOSFET transistor, metal oxide semiconductor field effect transistor. To determine if it's operational, first of all, note that it has 3 legs. This is the front of the transistor. You'll see this has an indentation to the heat sink portion of the transistor. The back of the transistor is flat. The legs are numbered from left to right, 1, 2, 3. 1 is called the gate, 2 is called the drain, 3 is called the source. The transistor acts like a switch. We'll use the continuity setting on the multimeter to verify its operation. If we give the gate 0 volts, then we have an open circuit between the drain and the source. If we set the gate to 5 volts, then we have a closed circuit between the drain and the source. And the source is connected to ground when you make these measurements. This is the operational amplifier, or op-amp. It's the LM741. It's probably the most basic op-amp. You can see at the top of the op-amp we have a little indentation and a little circle that indicates the top of the op-amp, and then the pins are numbered 1 through 8 counterclockwise from the top. So if this is the top, here are pins 1, 2, 3, 4, 5, 6, 7, 8. There's no connection to pin 1. Pin 2 is the inverting input. Pin 3 is the non-inverting input. Pin 4 is the minus power supply, minus 15 volts. Pin 5, there's no connection. Pin 6 is our output. Pin 7 is our plus power supply voltage, plus 15 volts. And there's no connection to pin 8. So there are only 5 pins that we need to connect on our op-amp. Pins 2, 3, 4, 6, and 7. While the op-amp looks like a single component, and appears like a black box, we treat it like a black box. It has many, many transistors and resistors in it, which we are not particularly interested in at this point, since we are using the op-amp to perform certain functions. So we treat it like a black box, but we have to know how to use it and what its limitations are. To use it as a buffer op-amp, where the input will equal the output, we connect the input, or the non-inverting input, pin 3, to our input. In our case, it'll be 5 volts. We connect the output pin 6. We feed it back into the inverting input, indicated with this minus sign, which is pin 2. Pin 4 gets connected to our minus 15 volts. Pin 7, our plus 15 volts. And pin 6 is our output, which we measure should be the same as our input. This is the buffer op-amp configuration for our 741 op-amp. The second part of our exercise deals with the oscilloscope and waveform generator. You will choose on the waveform generator a 10 Hertz, 2 volt peak-to-peak sine wave with a 3 volt offset, and send it to channel 1 of the oscilloscope using a BNC cable. On the oscilloscope, you are to display 5 cycles of the input signal and verify the frequency, amplitude, and offset of the sine wave, verify that they are correct. To do that, you'll use your cursors and your measurement keys. And you will see that in the actual video of me performing this exercise. It's important that you set this voltage and time scales on the oscilloscope before inputting the signal. It's important so that when you actually input the signal, you get on the oscilloscope screen exactly what you set and what you predict. If you don't do this, when you turn the signal on, there's a chance you will get garbage and you'll have to start making adjustments on the oscilloscope. That doesn't give the people watching you perform this exercise much confidence in your ability to use this particular piece of equipment. So through practice and repetition, you'll become expert in the use of the waveform generator and oscilloscope, and that will leave a lasting impression on anyone observing you using this in engineering practice. Similarly, you'll choose a 10 Hertz, 2 volt peak-to-peak square wave with a 1-volt offset, send it to channel 1 of the oscilloscope, and again display 5 cycles of the input signal on the oscilloscope, verify that the frequency, amplitude, and offset are correct, use cursors and measurement keys, and again set the scope voltage and time scale before inputting the signal. In using the waveform generator with the oscilloscope, engineers often observe that the voltage they see on the oscilloscope is twice the voltage that they set on the waveform generator. The reason for this is as follows. The waveform generator, or here called the function generator, has an output impedance of 50 ohms. That's constant, that cannot be changed. The default setting on the function generator, what it expects is a 50 ohm load impedance. A voltage divider then is formed, and so what you measure at the output of the voltage divider is 1/2 the voltage that you set. So if you set 1 volt on the function generator assumes that you want 1 volt at the output. And in order to make that happen, the function generator will send twice the voltage that you set. And so that works well if your load impedance is 50 ohms. But the input impedance of the oscilloscope is 1 mega ohm. And so in place of 50 ohms, we place 1 mega ohm. Then essentially there is no voltage divider effect. And whatever you set, you will see at the output. And so if you set this to be 50 ohms for the load impedance on the oscilloscope, with the input being the 1 mega ohm input impedance of the oscilloscope, whatever you set on the function generator, you will then see twice that value on the oscilloscope screen. So how do you remedy that? Well, you remedy that by simply not setting the load impedance to be 50 ohms or allowing that default setting to persist. You simply replace that load impedance with what we call high Z and make that choice, high impedance. And in that case, whatever voltage you set on the waveform generator, you will then see on the oscilloscope. In performing part 2 of your Mechatronics introductory exercise, the question is, how do you set the time and voltage scales on the oscilloscope before you send the signal? Well, to set the time scale, we note that we're sending a signal, both sine wave and square wave, to be 10 hertz. The frequency f is 10 hertz. That's 10 cycles per second. The period t is 1 over the frequency. 1 over 10 is 1/10, 0.1 seconds per cycle. The exercise states that we want to show 5 cycles on the oscilloscope screen. 5 cycles then is 0.5 seconds. The time scale, the horizontal scale, has 10 divisions. 0.5 seconds divided by 10 is 0.050 seconds, or 50 milliseconds. So we need to set the time scale to be 50 milliseconds per division to show 5 cycles of our 10 hertz sine wave or square wave. On the voltage scale, there are 8 divisions. That's the vertical scale. For the sine wave, we set a 2-volt peak to peak with a 3-volt offset. For that, we should choose 500 millivolts per division. For the square wave, we send 2 volts peak to peak with a 1-volt offset. And for that, we should choose 1 volt per division. Thank you for your attention. Please see the video showing me performing each part of this introductory exercise.